Okay, folks, this lesson is Introduction to Accumulated Change, and it's sort of the start of your work on integration, which is a really powerful mathematical way of adding things up. So to start, let's take a simple situation. You're probably familiar with the idea that distance is equal to velocity times time. So let's imagine you take a trip at a constant velocity. You're traveling in a car at 50 miles per hour for a total of 3 hours. How far will you have traveled? You say this is a piece of cake. It's just velocity times time, 50 miles per hour times 3 hours. You could even think of the hours as canceling out here. That's 150 miles. Great. I just want to point out that there's a geometric or a visual interpretation to this. We could take your velocity curve, plot it, it's a constant, and we could imagine that we want to look at it from time equals 0 to 3 hours. And so going across the horizontal, this dimension here is 3 hours. Going up the vertical, this dimension here is 50 miles per hour. And if you kind of think about the area of this rectangle, you multiply, base times height, that's 150, and that's miles per hour times hours leaves you with miles. So in this case, the total distance you traveled was equal to this area kind of enclosed by the velocity curve during the time that you were interested in. Let's now look at a slightly more sophisticated example where your velocity is not a constant anymore. It's increasing according to the function 30 plus 10t, where t is your time in hours. But same question as before, how far will you travel in the first 3 hours? And what we're going to do is just make an approximation. And the approximation is that we're going to look at your car at the end of each hour, and however fast it was going at the end of the hour, we're going to pretend that that's how fast it was going the whole time. So at the end of the first hour, we look at your car and it was going 40 miles per hour, we're going to pretend that was the velocity the whole time. Okay, at the end of the second hour, you were going 50, we're going to pretend that that was your velocity for that whole hour. And at the end of the third hour, we look up at our velocity curve, you were going 60, we're going to pretend that that was your velocity for that whole hour. And so we know what to do with a constant velocity for the first hour, right? You traveled 1 hour at 40 miles per hour, not really, but we're pretending, so you would have gone 40 miles. Second hour, you would have gone 1 hour at 50 miles per hour, kind of represented by this rectangle here, so that would be 50 miles. And then the third hour, you would have gone 60 miles per hour for an hour, represented by this rectangle here, that's 60 miles. And then you add things up, and 60 plus 50 plus 40 is 150, so we're going to say your total distance is 150 miles. Okay, this, of course, is an approximation. And when we look at this approximation, we can see that we made what's called an overestimate, right? We kind of took the fastest speed of the interval and pretended that was the speed the whole time. So that's going to overestimate for us how far we went. And the way you see that visually is that each of our little rectangles we drew, if you look at the corresponding kind of geometry represented by the blue curve, the rectangle we drew is kind of higher up. It captures more distance in it. Okay, so anyway, this is an estimate, 150 miles per hour. We can, of course, do the same thing, but instead of choosing the fastest speed, or the fastest velocity for the interval, let's choose the slowest one, which in this case is the one at the left-hand side. So for the first hour, we're going to pretend we went 30 the whole time. For the second hour, we're going to pretend that we went 40 the whole time. And for the third hour, we're going to pretend that we went 50 the whole time. And if you add it up, that would be 30 miles plus 40 miles plus 50 miles. 30 plus 40 plus 50 is 120 miles. And this one looks like an underestimate because we kind of took the slowest speed. So a very common thing that you might do is if you have an overestimate and an overestimate, you could take the average of them. It's half of 120 plus 150. That would be 135 miles. And that could be our estimate of the distance that you traveled. Now you could ask if we could even do better than this estimate. And so far we've been choosing 1 hour long chunks, but what we could do is choose even smaller chunks, right? Because over smaller chunks, it's like the velocity of your car changed less, so the assumption of a constant velocity might even be better. So instead of 1 hour long chunks, what if we did half-hour long chunks, and we'll do them maybe starting with the overestimate. Okay, so we're going to take a half hour, the first half hour here at this speed, and then we're going to take the second half hour at this speed, and we're going to take the third half hour at this speed, and so on, all the way up to the last one, which would look something like this. Okay, so we're going to have 1, 2, 3, 4, 5, 6 rectangles to add up. And here's how we could do it. If we want the area of rectangle 1, well, the width of it now is not going to be 1 full hour, it's going to be 1/2 hour. And then we've got to multiply by the velocity we took. Well, we took the velocity at the end of that half hour, so that's at time equals 1/2. So I could plug in 1/2 for t up here. I get 30 plus 10 times a half is 35. So 1/2 hour at 35 miles per hour is going to be 17.5 miles. Okay, then for the second rectangle, we could do the same thing. It's 1/2 hour. If we want to know our velocity, then since we're talking about this rectangle here, we need the velocity at time equals 1. We plug in t equals 1, we see that it's 40 miles per hour. So what we get out of that is 20 miles, and so on. And we can do the last one. The sixth rectangle is going to be 1/2 hour times 60 miles per hour. And that's 30 miles. And you can do the intermediate steps if you want, but if you add up all of these totals, you get an answer, and it's a slightly more refined answer than we were taking hour-long chunks. When we took these smaller chunks, one thing you might have noticed is that we're getting closer to just getting exactly the area under this blue curve. Like here we made an overestimate, but the little bits of our overestimate are smaller. And if we did 15-minute chunks, they'd be even smaller. And if we did 1-minute chunks, the overestimate would be even smaller. It'd be a lot more work to do by hand, but it would be a more exact answer. So I'm trying to get you towards this idea that the total distance traveled is just the area under the velocity curve. So let's try to do this exactly. If velocity is positive, the total distance traveled between two times is just the area under the velocity curve between those two times. So you're riding on a bicycle where your velocity is 5t feet per second, and t is measured in seconds, and the question is how far do you travel from time equals 0 to time equals 3? Well, what you have to do is you have to imagine that we're looking for this total area under the velocity curve, right? The area of this rectangle. And you know geometry, so you know that the area is going to equal 1/2 times base times height. So that's going to be 1/2, and the base is 3 seconds. And the height, well, that's this height here, which happens to be the value of the velocity at 3 seconds. At 3 seconds, you're going 15 feet per second. So this side is 15 feet per second. The seconds cancel out, and you end up with 22.5 feet as the total distance you've traveled. And notice that this is exact. This is not an approximation, and it's because you exactly found the area under this velocity curve. So now remember more generally, like what's the relationship between position and velocity? You might recall that velocity is the derivative of position. So what you've done in this problem and in the preceding problems is to find a total distance or a total change in distance. What you did was basically cumulate the velocity over small intervals. Let me say that again. To find a change in distance, you cumulated the derivative of distance, which is velocity. And I want you to start getting that general idea in your head, that to find the total change of something, what you have to do, or one thing you can do, is cumulate the rate of that thing in order to find the answer. Accumulate the derivative of that thing. So let's do this again in an example. This time it's about population. So a city's population grows at 5,000 people per year. That's a rate for 3 years. And then for the next 4 years, it grows at 3,000 people per year. So I've plotted the rate for you here. It's constant for 3 years, and then it jumps, and it's another constant for the next 4 years. And the question is, what is the total change in population in the 7-year period? And what you have to do is in mathematical terms, you have to cumulate that rate, or geometrically, you got to find the area under this stuff, right? So we're going to basically think of having two rectangles, R1 and R2. And for R1, what we have is 5,000 people per year for a total of 3 years, and that's equal to 15,000 people. And then for the second rectangle, we're going to have 3,000 people per year for a total of 4 years. And so that's equal to 12,000 people. So if we add up R1 and R2, that's 27,000 people. So the answer is that the total change in population is 27,000 people. And what's crucial, again, for you to understand is we got a total increase or a total change in population by accumulating the rate of the population. So let's wrap up. You should ask yourself if you can estimate total distance traveled from a velocity function, if you can use over and under estimates to approximate a total change or a total distance, and if you can explain how to find the total change of a function given the rate of change or given the derivative. All right, thanks for listening.